Assalamualaikum warahmatullahi wabarakatuh to all of my respected students. Now we will move to the next topic, which is chapter 7, Principle of Chemical Equilibrium. At the chapter, we will see where the chemical thermodynamic is used to predict whether a mixture of reactant has a spontaneous tendency to change into products, and then we use it to predict the composition of the reaction mixture at equilibrium. And lastly, we use this knowledge, or we use this method to predict how the composition will be modified by changing the condition of the reaction. So before we move to the next topic, let's recall what is equilibrium. So when we talk about equilibrium, equilibrium occurs when two opposing forces occur at the same rate, and at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So we can see that, we can see from here, let's say this one is a reactant, so this one is a product, where the rate of the species change is the same. So thus it make the concentration here is the same. So to recognize equilibrium in any graph or in data, we can state that first, they equal rate in both forward and reverse reaction, like this animation, and also second, have a constant concentration of the reactant and also the product. So for the spontaneous reaction, we can state that the delta G is less than 0. We already know that the formula of our delta G is delta G equal to enthalpy minus temperature delta entropy. And also from our previous lecture, we already see that for delta G we have there's a few derivation or derivative of the delta G. So you can refer to previous video and my previous notes. So everything stated how to derive a delta G from a given condition and also a given situation. And at a constant temperature and pressure, a reaction mixture tends to adjust its composition until its Gibbs energy is at a minimum. So let's see this graph. This graph shows the variation of Gibbs energy of a reaction mixture with progress of the reactant. So pure reactant on the left and pure product on the right. So if we look carefully at this graph, here is a very little of the reactant convert into a product before G has reached its minimum value and the reaction doesn't go, or we call it reaction unable to proceed because of what? Because the energy of a product for this line A, for this line, the energy of a product is more than the reactant, so net energy is less than 0, because we need to refer back to our formula is the when we talk about delta G and equal to G product minus G reactant. So we want it to be less than 0. So if we have a positive and negative. So of course, if the value is bigger than this, if GP is more than GR, so of course our delta G is more than 0. So that's why this reaction is unable to proceed, or we call it disable, does not go. However, if our delta G here, G product is less than G reactant, so we will have a delta G is less than 0. So that's why we can say that this reaction is able to proceed. Where for B, reaction reach equilibrium. So this thermodynamic data can be used to predict the equilibrium composition of a species present in the reaction. Either this one, either it is a reactant or product, and how the composition here is reactant or product depends on the condition of our setup or our experiment. So for the reaction, let's say about the reaction gives energy. Okay, I do have two example here. Okay, for the first example is the isomerism of glucose 6-phosphate, or we call it G6P, the fructose 6-phosphate or F6P. So this process we call it glycolysis. So here is the molecular structure of glucose 6-phosphate, and here is the molecular structure of fructose 6-phosphate or F6P. Okay. Once this chemical reaction, this reaction undergoes a chemical reaction, what happen is this amount, this G6P will be converted to F6P. So thus what happened here is the amount or the concentration of G6P will be decreased, and the amount or the concentration of F6P will be increased. So that's why the change, we have a delta net change, or the concentration of G6P will be increased. That's why we put a negative value, while we put positive value at the F6P, because the concentration will be increased. So this is what happened to a reaction. So this we can say that amount of substance changed by the delta N, and also the contribution of substance to total gives energy of the system changed by its mu, or its chemical potential. So the net change in the gives energy of the system, we can say that delta G equal to delta G product minus delta G reactant. So here we can have a chemical potential of F6P, or fructose 6-phosphate, times delta N, because it is our product, and chemical potential of G6P times delta N, this because this is our reactant. So if we able to factorize this one, we will have minus mu. So that's why we can move the delta N to this our left hand side. That's why we'll have this final equation, where delta Rg or delta given energy at a given reaction equal to delta G over delta N, equal to chemical potential of F6P, or chemical potential of a product, minus chemical potential of a reactant. So this is the first example. So if we plot it graphically, what we will have is we will have this kind of graph. So to find the delta Rg, what we need to do is we need to calculate the slope of the graph here, and then to find it what we need to do is, here is delta G, here is delta G, delta N. So if you still remember, if we have x1, y1, here is x2, y2, to calculate it, to calculate the m, what we need to do is y1 minus y2 over x1 minus x2. So if we refer back to our graph, here will be delta G, and this one will be delta N. So this is how we get the delta G from our graph, and we can get the data. We can get this delta G by using graph, or by using chemical reaction. So it depends on you how to get graph. So I already proved it how to get this relation, this relation.